So good morning, everyone. My name is Fu. So basically, I'm hosting this the last keynote speech of today. So for the presentation today will be on the title of Extreme Edge Intelligence, Moving AI Sense Closer to the Senses. So the presenter is Professor Amine Bermak, Professor and Associate Dean, College of Science and Engineering, CSE, Hamad bin Khalifa University at Qatar. So this is a brief introduction of Professor, because Professor has a very long biography, so basically I did a brief summary. So Professor Amit Burma has earned his master's and PhD in electrical and electronics engineering in Paul Sabatier University, France in 1994 and 1998. He held various academic positions worldwide, including roles at professorship at HKUST, Edith Howard University, and York University. Currently, he serves as a professor and associate dean at Hamad bin Khalifa University quarters. So Professor Burma has pioneered contributions in many areas in low power sensory wearables devices, oscillations, visions, and AI. So later on, this is about the topics that he'll be presenting on his keynotes. He's actually received many awards, including 5 Best Paper Awards and Michael G. Gailey medals and multiple teaching and innovation awards. With more than 13 patents and 500 publications, he has supervised more than 40 PhD and master students and actually developed more than 50 IC chips. So with all this achievement, he also worked very closely with industry, including Motorola, Intel, British Aerospace, and many, and secured more than 20 million of research funding. And he also been a very active cast members, have been serving many editorial boards in our IEEE journals, and actually is our distinguished lecturers and fellows of our IEEE and AAIA. So we actually welcome Professor Bermak to give his talks on this topic again on extreme edge intelligence, moving AI closer to senses. Thank you.
All right, okay. Yeah, first of all, I would like to thank the organizing committee, particularly Dr. Sam Tang, for inviting me today here. Today, my talk is going to be related to basically extreme edge intelligence. When we talk about edge intelligence, basically we mean that we move some of the processing at the sensor node. And in a nutshell, if I try to summarize what I'm going to talk about before I start, you will see whether I delivered the message well at the end. So if you know what you are trying to aim, typically when you sense, then you can design the sensor in order to help you basically achieve your objective. So for example, I'm going to talk about olfactory sensors, where the idea is not only to sense odors, but to classify them. So if I know that I need to classify at the end, instead of just acquiring raw data, the idea is to look for features right at the sensor level. And this will simplify your processing, it will simplify your AI, it will simplify all the post-processing that you will see. And I'm going to show you some examples of that in the olfaction area, vision area, and also recently have been working on wearable sensors. So in a nutshell, this is what I'm trying to do today. Looking at the sensor, trying to do innovation at the sensing level in order to detect features rather than just data. And once I have features, I can classify much better. I can implement my signal processing, machine learning much, much easier. So all of this has been motivated, of course, by IoT, where we know that IoT and in IoT sensors we are going to play a very major role. So you're talking about basically billions of devices that are deployed on the internet. If you compare that to Moore's law, so the number of IoT devices that are deployed on the internet is increasing drastically, even faster than Moore's law. And the market is supposed to grow at an exponential pace as well. So we're talking about billions, in the hundreds of billions of devices that will be connected to the internet. And there are a lot of opportunities in that area. And all of these devices will include sensors, for sure. You have to include sensors, you include also wireless communication and a lot of processing. And you need to do that at low cost, typically. So if we try to look at the categories of IoTs that we have today in the market, I can classify them in 2 categories. You have massive IoT and critical IoT. In the massive IoT, the volume is of importance. So you're talking about low cost, low energy, very small data volume, but massive numbers. You're talking about applications like, for example, smart building, logistics, smart meters, agriculture. We're seeing a lot of sensors deployed for agriculture today. And in these areas, of course, latency, for example, is not an issue, but volume and cost is very, very important. On another basically edge of the spectrum, you have critical IoT, and this includes applications like remote healthcare, remote surgery, intelligent transportation systems, where latency is important. You have to react very fast because you're talking about application in transportation, vehicles, and so on, and you need to respond very, very fast. And also reliability is a concern. So typically, when you look at the architecture of the IoT today, most of the storage and the processing is done in the cloud. So basically, these IoT nodes are just basically pushing data to the cloud. And if you're talking about video, you're talking about a lot of data. So which means that you need massive storage. You need also processing to be done in the cloud. Now we can find with the cloud, when you purchase cloud, you also have a lot of tools, AI tools and so on, that come with it. So most of the processing today is done in the cloud. So you look at conventional architecture today with 5G and so on. Basically, IoT nodes are just pushing data to the cloud. And you're talking about scalability is going to be an issue because you need to store a lot of data. Storage is going to be an issue. Bandwidth, especially for video, you're talking about very large bandwidth. And also energy and privacy because you are sending raw data. All right. So can we move some of that intelligence to the edge? And this is what we call edge intelligence today. So if you do that, it means that you need to move some of the processing to the edge, very close to the sensor. So if you do that, of course, your system is going to be more scalable, less storage, less bandwidth, because you make decisions locally. And more importantly, also privacy, because you're not transmitting all the raw data. You're just sending probably just decisions to the cloud. On the other hand, it is difficult because the architecture of the cloud is not designed to do that. And also the IoT nodes. You don't have powerful processors on the edge. And therefore, deployment complexity is going to be an issue. The infrastructure is not ready because you're not going to have a processor with every IoT node, and also limited resources and so on. So what I'm trying to do in this talk is really to show you that if you try to basically acquire features rather than acquiring data with the sensor, then actually you can do a lot of very smart processing. And the idea is to show you this for 3 case studies. I'm going to talk about olfaction, also vision, and also recently I'm working on wearable sensors. So basically, in a nutshell, if you look at the conventional architecture, you're talking about sensing. You do maybe a region of interest sensing. You do the ADC, you store the data, and then you process the data, including, for example, AI. Typically, you're acquiring the data from the cloud or basically from a memory. So the key idea here is, can we move some of these processing and make it closer to the sensor? And this is what we call edge intelligence. Of course, if you do that, then the benefits of that is going to be huge. You're talking about more functionality and flexibility because you're doing that at the edge. You're talking about low latency because you don't communicate with the cloud. Lower overall power if you optimize your system. Of course, faster operating speed, real time. Lower bandwidth, very low bandwidth. Actually, sometimes you only send decision. And also smaller memory at the edge. All right. Now, I'm going to try to show you that, as I said, but it's going to be mainly looking at how we can extract the right features right at the sensor level. And to show you that, let me start with this example of olfaction, where actually in my group, we design a MEM structure, which is a tin oxide sensor. This is for gas sensing. Typically, this is a MEM structure where you have basically suspended MEMS. You have a sensing film. You heat this film. Typically, it's tin oxide. And when you have odorous molecule that will deposit on the sensing film, you have an oxidation reaction at high temperature. And this oxidation reaction will give you variation of resistance. So by measuring this resistance, you can actually detect different smells. Of course, it's not very selective. It has a lot of problems. And therefore, in order to make it more accurate and more reliable, what we did in my group, we designed, based on this structure, we designed an array. And in this array, we included different catalysts, like PT, PD, and gold. And also, we added different doping for each of the cells. So we end up with an array, and the idea is to have a fingerprint type of sensing rather than just one single sensor, because these sensors, they suffer from a lot of imperfection. So when you have an array, then you can process it as basically an AI fingerprint at the output. All right. If you look at actually if you study these sensors, they have been studied very extensively in the literature, more than 30 years of work in this area. And if you look at a very old paper, 2008, you look at the response of tin oxide sensor. Typically, they're characterized by a power-law relationship. This C is the concentration of gases. This alpha and gamma are parameters that depend on the sensing film, but also on the gas that you try to detect. So if you try to use the sensor and look at the resistance variation, you are faced with calibration issues, and also you need to measure, be able to control also the concentration very accurately. Because in order to extract these parameters, you need to do experiments, and you need to control this concentration very, very accurately. This is typically not very easy. So now I'm going to show you what we did in terms of feature extraction in order to simplify the classification. Because at the end of the day, we don't want just to sense, we want to classify different orders. So assume that basically you're looking at one given output, which is a resistance. If you do the log of that relationship, of that resistance, you end up with additive term with respect to the concentration. And therefore, if I'm using one of the sensors as a reference, and I do it in a differential way, then you can get rid of the concentration. Basically, typically what I'm looking at, I'm extracting the log, I'm taking one of the sensors as a reference, and I always read in a differential way. Now, if you do that, then your parameters will become independent to concentration, and accurate measurement on gas concentration is therefore eliminated. Now, in order to classify, it would be nice to actually generate a spike, and this spike will be generated from each of these cells. So I'm going to assume that I have basically simple neurons, and basically each of these cells is going to give me a spike. Why a spike? Because later I can use a spike encoding in order to detect. And therefore, my architecture becomes very, very easy because I can classify just by looking at the pattern of these spikes. So to summarize, I will take the resistance, I will take the log of the resistance, I will generate the spike, and I do it for each cell. Therefore, I end up with an array, and this array is going to respond is going to give me an encoding. That will be a spike encoding. Very simple architecture. Now, it turns out that this works extremely well. I'm going to show you how we did implement this architecture. So again, to summarize, you have a gas sensory array. You basically expose it to a given gas or smell. Then what you do, you generate a spike that is proportional to the log. And basically, you get a spike pattern. And your recognition or classification is just spike pattern matching. So you can store these smells, different smells, and their corresponding spikes in a lookup table. And all you need to do is compare your spike train with a stored value in the lookup table. All right. So in a nutshell, this is what happens. So when you have an unknown gas, you expose it to your spike generator. You're going to generate these spikes, and they're going to happen at different time because you are using different sensing film, even though it's the same gas. Since I'm using different sensing film, different doping, and so on, these spikes will happen at different times. And what happens is because the enter spike is independent on concentration, it means that this time, or this sequence here, and this sequence, and this sequence, and so on, is independent on concentration, which means this pattern here would be specific to that particular gas. Now, if I change the concentration of gas, right, which is the C in the equation, what you get a shift in the same pattern. So the pattern, the spike pattern, will give you the gas, and basically the time to first spike, the time to first spike, or the phase, or the basically the shift, will encode the concentration of gases. So you end up with not only classifier, but also quantifier. You can quantify the gas, and you can recognize the gas in a very, very simplified way. I'm going to show you that this is really much more simple than you may think. So the idea is I have a sensory array. I convert that to a log. I generate a spike. I encode the rank order in a lookup table, and then I can recognize gases. Now, if you look at how we can, in a nutshell, implement this, you will see that this is actually very, very simple to implement. So it's actually a textbook of basically an undergrad. So how can I do that? You can imagine that I have my sensory array as variable resistance, and then I can have just an RC circuit where I charge a capacitor. If you charge a capacitor and then you discharge it, what you do, you monitor the time. The discharge of an RC circuit is the voltage is equal to the exponential of T over RC. So if I'm monitoring the time, it means the time is going to be proportional to the log of the voltage. What is my voltage? Ri. What is the R? It's actually my sensor. So I realize the log. I realize basically also the spike, because when I monitor the time, when I reach the threshold, I generate a spike. So it means that I generate the spike, and that spike, the time to that spike, of that spike, is actually proportional to the log. So very, very simple architecture, and you can do that with ADC free. You don't need any ADC even. So you can do it very low power, and this is summarizing how it works. It's ADC free readout. So based on that, we started actually, the initial implementation was just with the sensors interfaced with the microcontroller and the Bluetooth. This was actually the first version of our work. So you can see that it occupies a very small area. This is a sensor, and this is a microcontroller that does all the processing. And then later, we implemented it on chip. So also, it was interfaced with the personal handheld device on the laptop, and we had an interface where we can detect any gas. What is beautiful about this is that you can train the system to recognize new gases very easily, because you can expose it to a certain smell. You record the spike pattern, and you store it in a lookup table. And you get, basically, you can recognize a new gas. So you can train it in order to recognize new gases. All right, so this is actually the setup in my lab. So actually, this is wireless. We have the system here. And actually, we inject ethanol in the gas chamber. And then this is wirelessly connected to a handheld device. And we can quantify and classify the gases at the same time. All right. Recently, I have been trying to basically, that technique that you have seen, the drawback, I have shown you only the good things. The drawback is that it only works at high concentration, because that power-law relationship is only valid at high concentration of gases. When you go very low in terms of concentration, it doesn't work anymore. The other drawback, I started with the good things, I'm telling you the drawbacks now, is that it doesn't work very well for gas mixture. When you mix different gases, then that power-law relationship becomes very hard to model, and therefore it gets very messy, and you have overlap of spikes, all right? In order to overcome that, we try to basically increase our sensors by adding other features. Not only this domain encoding, but we try to actually add some other feature. And to do that, actually, one of my PhD students had his PhD working on basically a resonator-based gas detector, SAW and F-bar. So we use surface acoustic wave, and we coat it with different polymers that can be sensitive to different gases. So basically, you have your SAW device, and you coat polymers on top. And therefore, the mass is going to change when you have this molecule that this molecule of gases that deposit on the substrate. And therefore, your frequency, resonating frequency is going to shift. So we try to combine the two sensing mechanisms, where I have variation of resistance, but also variation of frequency. And we try to do what we call dual sensing mechanism. It turns out that this can help you a lot in order to simplify also the classification, right? So if you look at the delta F of the SAW device, you can see here, if you expose it to different concentration of different gases, you can see that you can clearly distinguish between the three gases. And also, if you look at the variation of resistance in the tin oxide sensor, you can see that also we have some kind of differentiation between the different gases. Now, what is really interesting is to try to combine these two sensing mechanisms. And if you actually plot the delta R over the delta F, which is the two sensors, you can see that your problem becomes linearly separable, which means you need a very simple classifier in order to classify between the different gases. As you can see, to distinguish between the three gases, I just need a linear classifier, right? Now, also, you can see how these two sensors work in a complementary way. So if you take, for example, methanol, and you try to use the delta R, you can see actually that that sensor works very well, because you can distinguish actually different concentration. If you look at basically the frequency shift, it's very noisy, which means basically here, the resistive type of sensor works better. If you look at pentanol, for example, another gas, you can see that the delta F works much better. So using the two sensors complement each other, actually, and then they can help you to distinguish between the two smells. In another recent work, actually, we have a patent on this. This is actually very interesting. I find it very interesting because my background is really, I have worked a lot on cameras. And when I moved to smell, I tried to use my expertise in the camera design. And we thought that there is a way, actually, we can design a gas sensor just like a camera. And the idea is actually to use basically floating gate process where you have two polysilicon. And the idea is just like in memory like DRAM and so on, like DRAM and the other type of non-volatile memory, they play on the threshold voltage modulation of the transistor by using a double gate process, right? So the idea here is to use the same concept in order to basically modulate the threshold voltage, but use it as a sensor. So the idea is to have the second gate of the polysilicon connected to the top layer of metal. On the top layer of metal, I will have interdigited electrodes in the top layer of metal. And I can coat that with polymers and different sensing film, which means that when you have these molecules that deposit on the top layer of the metal, you can modulate the threshold voltage. So that's the key idea. So this is what we did. Actually, we use floating gate, and actually we call it the gas FET. We have a very interesting patent on this. We call it the gas FET, just like ISFT, which is ion sensitive field effect transistor. This is gas sensitive field effect transistor. So the idea is to have floating gates. They are coated with different sensing film using interdigited electrodes at the top. And then you can use different structure of the interdigited electrodes. You can actually also embed temperature and also some heaters next to the sensor. Why heaters? Because actually, if you control the temperature, you can actually create virtual sensors. What does it mean? It means I have, let's say, N by M sensor. And then if I can control the temperature, I can build the third dimension of that. So I can sense at T1, T2, T3. And this will increase the number of sensors, and it will actually improve the classification later on. Because actually, if you look at the biological olfactory systems, they have actually hundreds of thousands of detectors, which means that we have a lot of basically smell detectors before processing the signal. If you look at what we can do in electronics, we are limited. I haven't seen more than 100 sensors at the same time. So the idea is to have not only an array, but also to create these virtual sensors in order to increase the number of sensors, have a large data, and therefore AI will be actually more meaningful. All right. What is really interesting about this is that we can use actually all the design techniques that we can find in camera design. So for example, we have a sensor array, a readout, we extract these features. We can do correlated double sampling, which is typically used in camera, CDS. Temperature sensor, we have an ADC, and all of this is done on chip. As you can see, we have even the ADC, all the control circuit is integrated on a single chip. So you can think about this as basically a smell camera. It's all done in CMOS. And the only thing you need to do is one step post-processing. Once you receive the wafer, typically you need to deposit these polymers, and it's just last step, right? So look at the results. It's actually very beautiful. It's really interesting. The smell becomes like an image. So this is, when we expose it to acetone, this is what we get. When we expose it to another gas, this is what we get. And actually, if you look at it, you plot it in a basically PCA or a 2D dimension, PCA, you can see that the problem is linearly separable. I can separate between the two smells. And what is really interesting is that you can use a lot of image processing techniques to process the data, which is today very mature. So basically, let me go back. So basically, it's actually very low energy, very low supply. Basically, we can have an array of these. We have designed 16 times 8, and actually you can increase that. We have a 10-bit SAR ADC, and this was actually one of the very good work that we have published, and it's actually patented if you want to look at the details. All right, let me move to vision. As I introduced you, I introduced at the beginning, I told you that my background is really related to vision and camera. This is where I started initially after my PhD. So what we are trying to do, actually, this is very recent work, is really to leverage our knowledge of the pixel in order to add intelligence so that we can simplify AI. Because AI today, you need to do a lot of convolutions. It's very heavy in terms of computation. It's very hard to integrate it together with a chip. So our goal is really to integrate AI together with the camera. And this is what we are trying to do. We are trying to leverage our knowledge of the pixel structure. If you take a PMOS type of pixel, which is basically the 3T architecture, very well known, if you connect pixels at the column level, you end up with a winner-take-all, because you have source followers, PMOS source followers. If you connect the source followers together at the bottom, you get a max. It's like a winner-take-all. If you use an NMOS type of pixel, and you have source followers that you connect together at the bottom, you end up with a loser-take-all. It's like you are calculating the min. Now, if you put in parallel with the photodiode, let's say just a transistor, a select transistor, and you do it repetitively, the overhead is just one extra transistor here compared to the normal APS, right? If you do that and you can control this switch, then actually you are summing these currents, which means I can do convolution. Now you're going to ask me about convolution. You need not only summation, but the weights. The weights are implemented in these control signals. So if I switch on this switch for T, I will have a coefficient W. If I switch this on for T over 2, I will have W over 2. So basically, by summing the current and controlling these switches, I can do any convolution. So based on this, actually, we are implementing, in fact, we are trying to patent a technology where we are implementing the whole thing on chip. So basically, all layers of convolution, the ReLU function, fully connected, layer at the end, and also the thresholding that is required, and everything is integrated on a single chip. But at this stage, we are doing a very simple architecture where we have actually 3 layers of convolution only. We can have a mask of 3 times 3. In our latest version, we can have 3 times 3, 5 times 5, and 7 times 5, 7 times 7. And basically, we are using very simple architecture and very little overhead added to the pixel in order to basically make the processing very low power and also very low overhead. All right. In another work, quite related, still talking about this idea of extracting features rather than data. So in a normal flow of processing in CMOS image sensors, typically you have the sensory array, you convert the data into digital, you store the data, and then you perform your digital signal processing, right? So typically, all your information is processed, or not information, I would say data. So which means that I'm doing the ADC on all the data, I'm storing all the data, I'm processing all the data. The key idea here is it possible to basically move some of these processing to the array level such that I extract features, and therefore I only turn on the ADC when I need it, on the features that I need. So this is what I call analog to information imager, or if you want, feature-based imager. And basically, the key idea is actually to look at the images and try to detect background versus edges. And if it is a background, you don't switch on even the ADC. We know that 80% of natural images are background, and therefore you're wasting a lot of energy for nothing. So this is exactly what we did. So we look at basically blocks of the image. We try to classify them into background or edges by looking at the mean and also the gradient of each block. And if you do that, actually, in terms of signal processing, if you simulate this in MATLAB, this is your original image. This is if you look at the blocks and only you keep the edges. You throw the background. And in fact, you compress more than around 10 times, because from 8-bit you go to 0.7 bit per pixel. And also, of course, you lose in terms of quality of the image. You're talking about a PSNR of about 31 dB. But for a lot of applications, this is OK. All right. Based on this, actually, we implemented the chip. And at that time, it was published in IEEE, and also we have a patent on this. And actually, basically, it achieved at that time the best power efficiency ever reported for any imager. So you're talking about something like 12 picojoule per pixel, which is really very, very low power. Because actually, naturally, you are saving 80% of the power right at the beginning, because you are throwing all the background images. All right. In another project, this project actually was with MIT. We had a project where the idea is really to have a network of cameras. And these cameras, preferably, are powered by energy harvesting, very low power. And the idea is actually to have all these cameras just monitoring features. And if you detect a feature, which can be motion or an edge, then you wake up the whole system, and you can, for example, transmit the whole image. So the idea is to have basically a network of cameras working together, just working in a very low power mode, just monitoring a given area, And actually, all of that is basically fused, or you have sensory fusion at the controller center. So basically, you're detecting only feature or edges or motion. And whenever you transmit to a control center, the control center will tell you, give me the whole image, give me the full image, give me just the feature, and so on. So it's like a feedback loop, and it's all controlled by a base station. So based on this idea, actually, we implemented what we call multimodal CMOS image sensor, where the idea is to do different type of basically motion detection, like frame differentiation, background subtraction. We also did the LBP, edge extraction, and all of this processing is done with compression as well. So all of this was implemented in a single chip at very low power, and the idea is to extract only feature, to detect only motion, and whenever I need, I will transmit the whole frame. All right. So these are some of the results. So for example, we did the LBP, edge detection, we did the frame differentiation, background subtraction. All of that was done in a single chip. And we can also implement imaging. We can implement region of interest or the full image. And as you can see, this was actually also a state of the art in terms of energy achieved. It was published also in JSCC and some other venues. All right, let me move now to the third case example. How much time do I still have? 20 minutes? With a question or without? Right, okay. All right, it looks like I have been moving quite fast. All right, so some time management now, I will go slower. So now I'm moving to wearable sensors. In fact, I started this area when I moved to Qatar, because actually this is a new university. It's a graduate university. Actually, when I went there, I started it from zero. And that's why I was motivated, because I started from a piece of paper. Basically, there were no students, no programs. I moved together with the dean also from Hong Kong, and we started the whole college. It's graduate level university, and now it's making progress. So when I moved there, I didn't have any clean room. I didn't have any lab. So the easiest start to basically start some fabrication is to do wearable, and this is exactly what I did. So instead of going through photolithography, having a clean room, and so on, I really tried to establish inkjet printing and also printed electronic facility. And this is what I established in that lab. So now we can do actually a lot of different type of printing. Of course, printing of single layers, but you can actually use these layers in order to do very, very interesting things. I'm going to show you some of the work that we have done very soon. All right, so these are the facility that we built, substrate treatment, some manufacturing tool with inkjet printing, and also very good characterization lab that I have there in HBKU. All right, now when you print single material, let's say on a substrate, any substrate, it can be fabric, it can be plastic, it can be anything. You can build very interesting sensors. And in fact, for example, you look at temperature sensor, it's just a resistance variation of a wire. You apply a current, resistance variation of that wire will give you somehow proportionate temperature. You can do humidity sensor by having capacitive, basically type of material where you have a dielectric, and that dielectric is sensitive to humidity, let's say. So you have a capacitance, and because the capacitance, the permittivity depends on the dielectric, therefore you can detect humidity. In fact, we try to build also this cough sensor, respiration sensor. We did it during the COVID. So the idea was actually to design a smart mask, and I'm going to show you how we did that. You can also detect some VOCs, looking at electrochemical sensing, and you can do that actually also with single material deposition. So it may look very, very simple because you are depositing only one layer. Typically, it's micro scale. This inkjet printer, you can actually design a pattern on any substrate on a micro scale. But it's not very uniform pattern, which means these sensors are very dirty sensors. They respond to everything and anything. So actually, we try to build the temperature sensor, and we try to use it for a smart mask. So basically, wearable, and you have the sensor there printed on the mask. Turns out that when you bend the mask, the resistance is going to change also. So if you look at the mechanical stress of the sensor as you bend it, right? You don't know whether it's temperature or whether it's mechanical stress. So that's why these sensors, as I said, are very, very inaccurate. I call them dirty sensors. They can respond to anything. So the innovation has to be in the architecture, in how you can have reliable sensors out of these dirty sensors. So for example, we have a patent, and also we deploy this in our smart mask. So the idea is actually to print this sensor on both sides of the mask, of the fabric. And therefore, when you bend one side, you stretch the other side. And therefore, they will respond in a differential way. One sensor will have the resistance increasing, the other will have the resistance decreasing. If you do it in a differential way, then basically you cancel that sensitivity to bending on mechanical stress. So as I said, easy to fabricate, but you have to compensate for a lot of issues, and that's where the innovation is. That's where you can file a patent. It's not on depositing just this material and so on. All right, so in my group, we don't do just the sensor, we build the whole system. So we go from the sensor to the readout to the ADC. Sometimes we do it microcontroller, sometimes we build our own chip. And then going all the way to the software and also how to handle the data once you collect it. You're gonna ask me why I'm talking on this in extreme intelligence type of AI. Because you're gonna see actually wearable, if you combine them with AI, it's a very powerful tool actually. You're gonna see it very soon. So this is the smart mask that I was talking about. So for example, it can detect vital signs, such as the body temperature, because you're breathing, your air breathing, you can measure the temperature, respiration, cough, and even location. Actually, we did that. We have also some publication and a patent on this. This is actually a smart diaper, where the idea is actually to measure the temperature of the baby. It measures whether the diaper is wet or not. There is a humidity sensor there. And also there is a strain sensor that measures the breathing of the baby. So you will actually detect very accurately his breathing pattern. All right? Oh, it's going backward. All right, so also this can be used in what we call skin electronics. Wearables there is actually a lot of very active groups, especially in Japan, working on skin electronics. So the idea is actually to put these patches, and these are strain sensors. They have a resistance that vary with the strain on your skin. And just imagine that you map all your face. In this group in Japan, what they did, they put these sensors on the face, and as you talk, you have different muscles that are moving, and actually they can recognize the speech just by looking at all these strain sensors, which is very, very interesting. So you can imagine AI together with this type of sensors is going to be, the limit is going to be the sky. So this is what we did in my group. Actually, we purchased this, what we call decal substrate. These are substrate just like tattoo. They stick to the skin. And I asked my postdoc to characterize them. And you will be surprised to see that these substrates, which are called the decal substrate, they are actually very robust. This is actually testing them with different strain over multiple cycles. He did a test over 500 cycles. It's very stable. And with an increasing strain over something like 1,000 cycles. And it gives you a response which is variation of resistance and which is very, very stable. So using these sensors, actually, or this substrate, you can build actually wonderful sensors. So for example, my postdoc, we have a demo in my lab where we put this in a jacket. And as you wear the jacket, actually, you put it very tight. If you have it on your elbow, then you can detect actually all the movements. And it's connected to a laptop. So the idea is, as you bend your elbows and you do different joint movement, you can actually detect them very accurately. We put the sensor on the knee, and as you can see, we have different pattern for different motion. So for example, extending and flexing, walking, jogging, jumping, squatting and jumping gives you different pattern. And therefore, if you have a tight, on-skin tight suit, you can detect all the biomechanics and motion. You can imagine with AI, this will be very, very powerful because this is very low-cost sensors. All right, he actually experienced with putting these sensors on the thyroid bone, and you can detect whether the person is coughing, swallowing saliva. On the cheek muscle, you can see if it's showing, for example, on the forehead. If you put it on the forehead, actually when you look down or up, there is different set of muscles, and therefore you can detect whether the person is looking down or looking up. All right, this brings me to the conclusion. So in this last part, actually, I didn't do AI yet, but the potential of having AI combined with the sensor is actually very, very powerful. So in conclusion, I would like to say that IoT is going to be a major market of the segment in the future of electronics. and microelectronic industry. I think moving intelligence to the edge is going to be very interesting and will result in a lot of basically a lot of benefits, including overall optimization of the system, optimized performance in terms of storage, power, and processing. You can have efficient processing. Like, for example, I have shown you that basically just by looking at the rank of the spike, I can classify, and I can train the system in a very simple way. And basically, we have demonstrated how edge intelligence can be achieved. Very complicated processing can be done in the analog domain, like, for example, this edge detection and so on. And averaging of pixel is done through photocurrent summation. The weighted sum is done through a select transistor. And edge intelligence is a very important path of research, I believe, for IoT, future IoT systems. And of course, there will be a lot of hurdles and difficulties, but this is what we need as researchers. And with that, I would like to conclude my talk. Thank you very much.
Hello. Okay. Okay, so fast. Okay, good. You can turn on the mic on your right hand or left hand side.
Sure. Can you hear me?
Yeah, sure.
Hi. Yeah, a very interesting talk. Thank you very much. So, if the sensors are, on the wearable, do you think you can put enough compute, basically, close to those sensors to do some real AI processing there?
This is for the wearables?
Yeah.
But for the wearables, I showed you just a good story. The problems we are facing is really the interface between wearable and non-wearable. Wearable and solid. Let me use this one.
Oh, yeah.
Yeah, I didn't have time to go through the drawbacks. Typically, when you don't have time, you just go through the advantages and the good news. So one of the problems that we are facing is really the interface between wearable and the solid. Because you need to communicate that data, you need to read it. It's a variation of resistance that can be on a soft, let's say, substrate, let's say a mask. But then to connect that to something that can wirelessly transmit the data and also convert it to digital and so on, you need a chip. That part is the hardest, especially the connection. So I think we are not at the AI level yet, and we need to solve this issue first. So in my group, we are examining different solutions. And for example, you will have these sensors here, and then we will have like a fabric type of connection, and then we will have just a chip that you can put on the top. Of course, if you have a chip, then you can include some of the AI, if the AI is simple, like the gas sensor processing I have shown you. But most of the time, it's quite complicated processing. Yeah.
Thank you.
I hope I answered your question.
Yeah,
but
you did.
Yeah.
Thank you.
We move on to the next question, Professor Water.
Well, thanks for a wonderful talk, Amine. I have two questions, actually, if I may. But I think we still have a bit of time, because you indeed did not overdid.
I just need to take my flight.
Okay. The first question is would there be any room, I guess so, for flexible electronics? This is a question that you should have asked. So, for instance, can I do polymer electronics? Because especially when the parts are moving, eventually you still need to connect it to a CMOS chip, which can be very powerful. But what would be the trade-off? Can you also use polymer electronics and basically have a low-cost sensor that you can turn into disposable?
Right. Yeah, so of course, you can do that. And I have seen even some sensors based on active devices, because all of these devices are based on resistance variation and capacitance variation. But I have seen, for example, glucose detectors that use polymers and basically active devices like a transistor. But it's not very reliable yet.
Yeah,
so most of these sensors are still very inaccurate.
Yeah, that's true.
So you need to add a lot of. That's why having an array of them and then adding the power of AI will help a lot, in my opinion.
Okay.
Yeah.
And the second question was, you mainly concentrate on resistive sensors. The drawback of the resistive sensors is that they consume power, they dissipate. Is there any, are there the developments in the field of capacitor sensors, for instance?
Right. That's a very good question. That's why actually we moved to the gas FET. With the resistive, it's true that you consume a lot of power, especially that you need to convert that resistance into a voltage. Typically, we do it through a voltage divider, and that part consumes a lot of power.
Yeah.
So doing it with threshold voltage modulation is probably at least 10 times lower power. So I have seen some development in that area, moving away from resistive. But the resistive, I really like it because of the processing. The processing part is very interesting.
And you're
yeah.
an expert.
Yeah, yeah, yeah.
Okay, thank you very much.
Yeah.
We still have a couple of times.
A very impressive talk. I am curious about the strain gauge when you put on the sensor put on the body. Actually, when we implement this experiment, we find the time domain is on the sensor signal is actually very complicated. But I saw when we implement the AI, actually we don't know what's the ground truth because every signal is mixed. But I saw your presentation. Actually, even though the bending and the classification is very clear, but you talk about you didn't use AI. What's the solution? Why can classification is so clear, even the bending and the muscle the change? Thank you.
Right, yeah, very good question. So for that, we are using actually some structure where when you bend, actually the morphology of the structure is going to change, and therefore you have variation of resistance. Where I have a material guy collaborating with me, so he's testing different material. But for the AI part, actually, we didn't implement any AI as yet. These are just very fresh results looking at just the sensor. So if you're asking me about the AI, these are just raw data. We didn't process any of these data.
How can you get a very clear signal, even you know the material, the possibility?
Yeah, so these are the raw data that we got. So typically it's a decal, this decal substrate. And I have one material guy collaborating with me. He's depositing experiencing with different type of material. And this is raw data that we got from these sensors.
Okay,
Yeah,
thank you.
yeah. I can give you more information about the material if you're interested. But it's really my collaborator. I'm not an expert on material, so yeah.
Yeah, we can go ahead for the next two questions.
Yes. So how does your camera concept compare to DVS cameras?
DVS?
Yes.
So we are using probably simpler processing units. You're talking about, let's say, can you go back just to be more specific on the question?
Event-based DVS cameras, which are very
Yeah, I know DVS.
common
Yeah.
in spiking neural network community.
Yeah, so for example, for the olfactory system, it's very similar in terms of processing to the DVS. But for image sensor, we didn't use any DVS. So for example, in the case of edge detection, we're looking at frame differentiation, for example. We're looking at basically more simple building blocks than DVS. We're not using DVS. Yeah.
Okay. Anyone would like to ask the last question? Prof. Samuel.
Oh, it's the last question? Okay, yeah. I mean, thank you for your talk. It's wonderful. So you talk about moving the intelligence to the edge, and we need to do some feature extraction.
Right.
But in our, I think, of course, in your experience, sometimes too many features cause problem because it becomes noisy. So can you comment a little on that?
Right. So basically, you need to be looking at how you classify. So you extract the feature with the vision that I'm going to classify later. So here, the log, for example, simplified a lot our classification, and also the fact that we generate a spike. So the feature here is just the log and converting that to a spike. Of course, if you increase the number of features, then the classifier becomes very complicated, especially if you don't have a lot of data. In order to increase the number of features, you need to have also a lot of data. So given the fact that we don't have multiple data here, we don't have very big data, we try to look at only one or two features in this type of process. Even for the image sensor, we look at the basically edges. That's all we did. And we look at background versus edges. So very, very simple features, but they simplify a lot the processing later on. Yeah. So the key is really what is your objective? How can you optimize the power, reduce the power? What are the features that I'm going to extract in such a way that I can do my processing simpler? So that's the thinking that we have when we did this work. Yeah.
You want to be the last guy? If not, I think Samuel will be the last guy to ask. So we're going to give the token appreciation to Professor